when I say like a triangle means change, so that means the change in x, change in y. Those are the actual changes in x and y on the curve, the original graph. So how much does x change, how much does y change between 2 points on the graph? When I say dx and dy, those are the changes in x and y on the tangent line. Okay, and I think the next slide does kind of have a picture as well to help illustrate this. So, here's my curve, that blue one. Between 2 points on this curve, my change in x, my change in y. If I were trying to use my tangent line, my x would be the same. So change in x and dx, those are going to be the same values. The amount you change in x on the curve and the line are the same. But is the change in y the same on that line? No. So that's where the dy comes in. That dy, how the y changes on the tangent line, that is the differential. So when I ask you for a differential, that is the dy, or it's our approximation to the change in y. Because if we are using the tangent line to estimate a point, we know that that point isn't completely accurate. So if I want to know how far off we are, that's like talking about the differential. Now keep in mind, when I say dy dx, that is the same thing as the derivative, right? So to approximate that change in y, we will just do the derivative times dx. So if I ask you to find the differential, that's like approximating how much our y would change. So we will take the derivative times the change in x. So the use for this, think about like in manufacturing. Okay, if you are making a certain part, and you have a machine to do that, will every 2 pieces coming out of that machine be exactly the same? No, there is some variability. But we need to know, okay, if I'm putting this part in and it could be off by 1/10 of a centimeter, how much will my final product be off? Because as it continues to go through, every step, it will be slightly different, right? So this idea is used to approximate like how much error would I have in my final product based on how much the original might be. If I'm having a machine to make bolts, okay, and I have bolts of different lengths, that could throw off my final product, or bolts of different widths. To some extent that's okay, but at some point it would not fit in the product that I needed to use it for. So we need to be able to kind of figure out how much would that throw off my final answer. So let's just look at a few examples of this. I want to compare the values of change in y and dy. So remember, change in y is on the true curve. Dy is, if we're doing our linear approximation, how much is that going to be off? And here's my function, and we're going to do it 2 different ways. As my x changes from 2 to 2.05, and then from 2 to 2.01. So first, we can find the actual change in y. If my x is 2, then my y would equal 9. And for my x is 2.05, I want the actual change in my y value. Okay, it is not a pretty answer. So the actual amount my y changes on the curve, we just subtract our ending point minus our beginning point. It's possible to have a negative for your change in y. That would just mean your value decreased. But here I'm seeing my actual change in y. My y amount should increase by 0.717625. So now, if I want to find dy, we need essentially our differential. Right, so let's think. Our dy dx is just our derivative. What's the derivative here? So dy is that times my change in x. That is the differential. I think the first couple of homework questions just ask you to find a differential. It's just that formula. The derivative with a dx on the end. Okay, so now to actually approximate our dy, we have to plug in our values. So our derivative, we are plugging in the beginning x value. So what was our beginning x? 2. Times dx. How much did x change to get to the end? 0.05. Okay, so in your derivative, we plug in the x equals 2, the starting point. Your dx is just a change in x. So it's like the ending x minus the beginning x. So it's like 2.05 minus 2. So that's where the 0.05 came from. Does everybody understand where those numbers came in? So now it's just plugging them in using our calculator. And what do we get? We get 0.7. So that means the actual change was 0.717625. But if we did linear approximation, we would have got a change of 0.7. So we can see how much error we have. You know, they're pretty close to one another. They're correct to one decimal place. So it's not too far off. All right, let's try it again with 2.01. I think I gave you one slide after this one. So, we already know that if x equals 2, y is 9. So when x is 2.01, plug that into the original equation so we can find the actual amount y changed. And you don't necessarily have to show me all this work, but I'm writing it out so you can see exactly where my numbers are coming from. So what is my actual change in y is our ending value minus the beginning value. So the actual amount y increased on this one, 0.140701. So if I wanted to estimate my dy, we already have the formula for it. 3 times my x squared, that's my beginning x, times, what is the change in x this time? Does everyone understand where I got my numbers? It's not that the math is hard, it's just keeping track of what it's asking for and what everything means, where we're plugging things in. So which one was a better estimate? The second one. Why would that one have been better? Our x's were closer together. Okay, the smaller the change in our x, the more accurate our y value would be. So I did ask you to compare it, so let's say, so the change in y and dy are closer together when the x's, when the change in x is smaller. And we already knew that, our linear approximation, it's only accurate if you're close to your x value. The further away from your x you get, the less accurate that's going to be. Any questions for me? So then I have one more example I'm going to look at. So the radius of a sphere was measured and found to be 21 centimeters with a possible error in measurement of at most 0.05 centimeters. So my radius is 21, but we know we're probably not 100% on that. So when I talk about error, that's like how much it could be off. That's like our change in R, or we could call it dr, because we know they're going to be the same. So my change in R is at most 0.05. What is the maximum error in using this value of the radius to compute the volume? Okay, so we know if we find the volume with a radius of 21, that's all well and good. But if the radius was actually 21.05, our estimate of volume would be off slightly. So what I'm asking you, when I say the maximum error, we're just finding the differential. So first we need an equation. We're finding volume. Do you guys remember what volume of a sphere is? So if I wanted the derivative, this is the derivative of volume, my variable is radius, so dv dr. You bring down your 3, you get 4 pi r squared. So my differential, all you do is get that dv by itself. So it's 4 pi r squared dr. That's the differential. So that will tell us how far off our volume is. 4 pi, what's my radius? 1 squared times dr. This is going to be a pretty big number. Let's go ahead and put the pi in as well on our calculator. So 4 times pi times 21 squared times 0.05. So if I want to know, that's my dB, that's how far my volume might be off. So the maximum error in our volume is about 277 cubic centimeters. So that's pretty significant. You know, if we're off by 0.05 of a centimeter on our radius, our volume changes by up to 277 cubic centimeters. So that kind of shows you how a little bit of error at the beginning can kind of explodes and turns into a much larger error at the end. And so if you were manufacturing and you said, well, that's not acceptable, what would you have to do? Go back and you would have to make sure your radius was more accurate. You would have to have less error in your radius to make your final measurement more accurate. All right, so that is the end of what I wanted to cover in this section. So just a side note on the homework, problem 35, it asks you to do a lot of different things. All I want you to do is the maximum error. It asks you to do like relative error in that as well, and I'm not talking about that piece. So you're just doing the max